Thank you for everyone who has joined the today's seminar. So today we have, before we start, actually, I have to remind people that these webinars will be recorded and all participants will be muted except for the panelists. But if you have any questions, please type in the Q&A box and I will help the speaker monitor the Q&A box. So today we have Dr. Zachary Fisher from Human Development and Family Studies at Penn State. He's an assistant professor. He's going to talk to us about penalized estimation of multi-way time series. So without further ado, Zach, take it away.
All right. Let's see here. All right, so can you all see that?
Yeah, yes, I can.
Okay. All right, so, yep, hi everyone. My name is Zach Fisher. I am a new assistant professor at Penn State. I'm a member of the Quantitative Developmental Systems Core, or Quant Dev, and my home department is Human Development and Family Studies. I want to thank Dr. Chow for allowing me to share my work with all of you. You know, I did just move to State College, so during these COVID times, I'm just excited to get the opportunity to share my work with some people across the university. In my talk today, I'm going to talk about a project that I started working on during my postdoc and have kind of continued picking away at over the last year. The project basically involves looking at new ways to model heterogeneous time series. And I call these time series multi-way here to indicate that I'm thinking about multiple multivariate time series, so typically collected on the same set of variables for different subjects. But here you'd have a multivariate data set, for instance, for each individual that you are considering. And yeah, by time series data, I'm basically referring to repeated measures of length greater than 50 or certainly greater than maybe 30, and will basically be operating in kind of the discrete time framework for all the proposed methods. All right, so to give a brief outline, I'm going to start by just kind of motivating this talk with some information about time series data, models, and heterogeneity. I'll talk about the n=1 vector autoregressive model, which is really the backbone model of the approach that I'm going to present. I'll then introduce the multivar approach and talk about two extensions, which are kind of in different stages of development. So yeah, I'd be excited to get feedback and hear what people's thoughts are. All right. So as a quantitative psychologist, that's my PhD training, and I postdoced in a population center and now work in human development and family studies. I've always kind of been fascinated with the relationship between individual level and cross-sectional perspectives, specifically in regard to this idea of heterogeneity and to the degree that it exists in many types of human behavior that we're interested in looking at. I always found this quote from John Nesselrode, who was a former faculty here at Penn State, to be really enlightening and just ring true, at least in my experience, which is the place of the individual in a science of behavior aspiring to establish lawful relations is somewhat ambiguous. And I really feel that on kind of a deep level. And I think that idea of heterogeneity really does create some tension in a lot of the dichotomies that we use to think about our world. So for instance, this idea of idiographic versus nomothetic modeling approaches, where we either focus on the individual or some group level process. The ideas behind kind of clinical versus public health, individual versus population health, or even thinking about bottom up and top down orientations in terms of, are we implementing a structural intervention, or are we thinking about this precision medicine, to kind of give two extremes of this process. And I think to a large extent, there are trade-offs between these different approaches, and neither is identifiable without kind of the informative contextualization of the other. So I think, both entirely have their place in our toolbox of methods. For me personally, I think the kind of common ground that I look for across those orientations is this idea that theories typically describe processes that unfold over time. So if you ask someone about their theory of a certain phenomena, typically what they'll describe to you is a process, not necessarily some kind of static model. And so to characterize processes, we typically require some type of time series data. Now, we're really lucky to be living in an age where kind of technological developments have really spurred a real boom in the availability of time series data. So just to give a few examples of some of the data that kind of comes across a social scientist dashboard, we have these ecological and immunological phenomena, so sensor-based physiological measures. And I think that this is expanding by the day in terms of different physiological measures that people are able to extract in kind of real time. Health and movement data, so calorie tracking, Fitbit, GPS. In psychology, daily diary or ecological momentary assessments are quite popular. Here, you'll kind of respond to some survey, either at random intervals throughout the day or kind of at targeted opportunities, usually collecting, I guess, measures of emotional states, even measures of social interdependence now in terms of like social network data. All these data types, becoming available in terms of really rich, a really rich temporal scale. And so I think with these new data types, we also have some new opportunities and some really interesting questions that we can look to answer. So for instance, the integration of multiple timescales and analyses is a really important open question. So how do we model processes that may unfold both moment to moment and longitudinally? Characterizing complex interactions across levels of analysis. And kind of the question that motivates a lot of my work, which is how do we characterize heterogeneity both between individuals and within individuals? And although I might be a little biased here, I do think some of the most exciting work in this area is actually coming out of the quant dev group here at Penn State. So to kind of just give a quick plug to some of their work, or some of our work, I should say. Peter Moliner, who's a pioneer in time series analysis kind of within the social sciences. He's currently kind of in the process of retiring, but he has a recent paper on new approaches to look at Granger causality with these intensive longitudinal data types. And you may all have come across these people and these papers before. Tim Brick and colleagues has developed the Wear It platform, which is this kind of mobile data collection platform for real-time monitoring, intervention, and analysis. And I know that's what kind of widely used across Penn State. Seaman Chow has been working on using control theory to optimize educational interventions. Zita Orovex has a recent paper on Bayesian continuous time models. And then Mike Hunter, here's some recent work on forecasting linear and nonlinear dynamics. And this definitely isn't meant to like provide any type of exhaustive picture of their work, but more just to give like a kind of rough sampling that might pique someone's interest. And if it does, I would definitely recommend reaching out and contacting them. Okay, so as I kind of mentioned, personally, the most interesting methodological questions for me are related to this idea of heterogeneity. Heterogeneity is defined as kind of the quality or state of being diverse in character or content, which is a fairly ambiguous definition, I think. But at the same time, when we think about time series data, I really do think we're forced to confront this idea of variability in a way that we just don't have to when we're looking at kind of cross-sectional or even kind of longitudinal data. I've even been thinking about lately how even the notion of how we would characterize heterogeneity, either within individuals or across individuals, is quite a difficult task. We have the data level, we have a model level, we have univariate, bivariate relationships across multiple variables, different measures for assessing those relationships and dependencies. We have potentially different functional forms, different magnitudes of parameters. And so I think, yeah, that's just to say that I think it's a complex question, and one that I'm definitely myself interested in not necessarily answering, but pursuing. So I tend to think about heterogeneity in kind of two broad overlapping dimensions: heterogeneity within individuals. So how do we model relations that may change over time? And in a related, way, how do we take into account kind of the deep context dependencies in our behavior? Because I think, these are often overlooked even in a lot of kind of the intensive longitudinal data scenarios. And so like within this heterogeneity, within individuals domain, we find ourselves, talking about non-stationary data, potentially time-varying parameter models, some way of accounting for that type of non-stationarity. And then for me, the big one and the kind of topic of today is heterogeneity between individuals. And so some of the questions I'm interested in is how can we leverage cross-sectional information to improve modeling of the individual? How can we identify temporal patterns that might generalize to the population? And then how do we also kind of retain, while doing that, retain the reliable individual level features relevant to the processes that we're interested in studying? And so in terms of the modeling question, and this idea of kind of between person heterogeneity, I think there's a bunch of ways you can kind of slice this cake. So some of the kind of things that I've been thinking about specifically are the type of heterogeneity allowed. So I kind of see this as there's certain approaches which allow quantitative differences in a model specification. So you may have kind of a random effect or impose some parametric distribution across a shared parameter, for instance. You also may have qualitative differences. So this means maybe the model specifications themselves are kind of qualitatively different depending on the individual that you're looking at. Then you can also think about like a modeling orientation here in terms of bottom up and top down. Are you starting with the individual, kind of fitting models, and then looking at how to synthesize that information versus starting with kind of some global model, as might be more kind of like a multi-level context. And then I would consider that probably more of a top-down approach. But I think that there's definitely overlap in all of these kind of broad strokes. I also think about the idea of theory appraisal versus theory generation with these different approaches. The one I'll talk about today is probably more on the side of theory generation. There's also the kind of level of analysis. So there's this idea of like identifying kind of common and unique variation, but then you can also think about groups, subgroups, and individual level dynamics too. So kind of, whatever the frame of reference might be for starting to think about heterogeneity. If we think about models, I think it's also useful to kind of just quickly think about models and where some of these things fall in current modeling approaches. And so, when you think about grouping individuals with similar dynamics, you can think about things like mixture modeling or clustering, community detection. Here you're trying to find groups of individuals with similar dynamics in terms of the process of interest. I mentioned multi-level approaches. So there's a multi-level VAR modeling, vector autoregressive modeling, is becoming quite popular. Here, typically you're interested in, you know, as I mentioned, kind of quantitative differences in certain aspects of the model, where you might want to know, is there variability in the autoregressive effect on this construct? And then this idea of common and unique variation. So I've highlighted two approaches here. Jive, which is just a really great name, is an approach that came out of UNC, where essentially there's a kind of a series of methods in development that came out of this original paper. But the idea is that you essentially can kind of decompose like multivariate data into these low rank joint and individual components. So you almost can think of it in terms of like factor modeling, where you're pulling out kind of a common and then unique aspect for each individual in the sample. So it's used a lot in like genomics, where you could have, you know, similar samples, different measures pulled from similar samples, things like that, but where usually the individual is kind of the linking factor. And then another approach, which is called group iterative multiple method estimation. And this is an approach that's in spirit very similar to what I'm going to be talking about today. And so I'll just kind of mention, GIMI was developed by one of my advisors at Chapel Hill while she was a PhD student here at Penn State. The idea of GIMI, or the objective of GIMI, is very similar to what I'm going to be talking about today, which is to identify essentially group level and individual level models from time series data. Now, the way that these approaches go about that is quite different. GIMI is based on kind of this forward stepwise path selection using modification indices in the structural equation framework. And importantly, it's based on the structural VAR model, which is actually a little bit more, which is similar to the VAR model that I'm going to be talking about today, but is a little bit more, I guess, highly parameterized and a little bit more difficult to model in terms of identification and things like that. But a really important model that allows for kind of directed contemporaneous relations. And actually, yeah, I should plug, I'll be giving, I think, a workshop through BERD in May. And so on GIMI, so that will be, if there's anyone who's interested in this approach, that could be an interesting opportunity. Okay, and so to quickly kind of just cover the objectives of the current approach, just to reiterate that. So the idea here is that I was interested in using structured penalties to try to cover these group level and individual level models. So taking this idea from GIMI, which was using kind of these forward stepwise approaches, can we do something similar with adding maybe some interesting features? So can we adjust for different levels of heterogeneity in the process, while allowing for qualitatively different models across individuals? So having real potential for really different structures when looking across individuals. This work kind of synthesizes three existing domains, or doesn't synthesize them, it borrows from three existing domains. One is kind of this vector autoregressive model, which is the backbone of a lot of multivariate time series models, and then constrained regularization and multitask learning. And there's probably a bit of overlap here in terms of both of these areas contribute to the idea of how do we share information across the individual models. And so here, taking the approach of sharing information through the parameters themselves. So actually putting penalties on the parameters as a way to kind of structure a relationship between individual models. So as I mentioned, the n=1 VAR model is kind of the backbone of this multi-VAR approach. So I'll just spend a little time talking about what that looks like for kind of a single individual's data set. I'll also mention some of the advantages and limitations of VAR before considering this case of having multiple individual data sets. Okay. So in economics, widespread adoption of the VAR in kind of the mid-1980s marked, I guess you could say, a beginning of a revolution in terms of modeling multivariate time series. I think more recently, this model spread out of economics, but that's definitely where it was originally used most often. Some of the really nice advantages of this unrestricted VAR model, it offers a really concise interpretation of time-dependent intervariable relations. So looking at kind of lead lag influence, it's really easily visualized using kind of path or network connection diagrams. And it potentially allows for the inclusion of many potentially relevant variables. So here I've kind of just structured a toy example that I'll mention throughout. Here we might imagine that we're measuring attention, fatigue, and hunger for a single individual, maybe let's say every 15 minutes across an entire day. We can think about those paths from lagged attention to attention as, or those, they're called autoregressive effects, as kind of measures of inertia, stability, or even regulatory strength. And we can think of the cross-regressive paths. So for instance, from fatigue to attention as, cross-construct influence or buffering. So a way that one process might influence the other in some time-dependent manner. Just in terms of notation, the VAR model is typically written as follows. Here we've specified a VAR model up to order P, where these phi 1 through phi p are the D by D transition matrices. Under some kind of some pretty general stability conditions, we can be guaranteed a unique kind of stationary solution to 1. And it's pretty common to estimate equation 1 using this ordinary least squares discrepancy function.
Zach, can I ask a quick question?
Yes, please.
In this case, D in your previous example is D equals 3. Is that correct? Okay.
Exactly. Yep. And I tried to be consistent throughout with that, but we'll see if I was. And then this slide is just here to point out that without kind of any loss of generality, we can specify a VAR-P model as in 6, and that's the notation that I'll kind of be using moving forward. But we'll be thinking generally about a VAR-1 model, so a lag 1, order of lag 1. But really, it doesn't matter. We could just as easily add lags, and everything that I'm going to talk about today would hold. So there's, it's actually quite popular model in the social sciences. It's been used to model things like binge eating behaviors, dynamics among mother-infant dyads. So in HDFS, one of the kind of big modeling areas that we're interested in these dyadic data analysis, where you're looking at kind of relations across people. So, mother and child, or peer relations, or family relations, things of that matter, trying to characterize kind of the interpersonal dimensions. Substance use patterns, depressive symptoms. So as I kind of mentioned, just a really broad workhorse model for multivariate time series. Now, one of the kind of main limitations of this unrestricted or canonical VAR model is that the number of VAR parameters grows quadratically. So as you start to, I mentioned as one of the kind of benefits being that it allows you to kind of include all the variables you're interested in looking at. But at the same time, that's not necessarily true, because as we start to include more variables, fitting this model starts to become a problem. And so in a series of papers by Basu and Michaelides, they looked at applying the lasso to this vector autoregressive model, basically to overcome this problem of over parameterization. Which are, and they establish a lot of like theoretical properties of the estimator and things like that for these dependent data situations. And so, when we start thinking about applying something like the lasso to encourage sparsity in this model, we start to think about potential advantages, including kind of this interpretational advantage, where we may end up with a model that's just easier to interpret. The idea of kind of bet on sparsity, which is that if you assume that the true signal is sparse and fit a model that accommodates that, you can recover the sparsity. If in fact the phenomenon is not sparse, it will be difficult to recover anyway. And so this is kind of one of the ways that people have talked about this sparsity principle. I think I may have butchered that. In computational efficiency, like I said, you really do run into some kind of numerical problems with that VAR model when you start going into higher dimensions. Just in terms of our kind of toy example, when we think about a canonical VAR, right, we're estimating all of those intervariable relationships. When we think about a sparse VAR, we're recovering kind of some sparse solution on those phi matrices in the transition matrix. Okay, so now kind of getting to the multi-VAR approach. So what happens if we move from the situation where we have a single individual to the situation where we now have multiple individuals who potentially have big structural differences in terms of their data generating models? And so here, right, this is 3 variables. We might think like, this does not seem that complicated, like fit a multi-level VAR model, and really it's not going to be a huge issue in terms of loss of or in terms of maybe different conclusions that you derive at. But when we start thinking about larger numbers of variables, larger numbers of people, it actually turns out to be quite a difficult problem in terms of allowing for these kind of structural heterogeneities in the modeling context, while also fitting some type of unified model or estimation framework to these different data sets. So, this is kind of like the main idea. I think I was gonna say I already messed up the notation, but I think it's okay. So this is kind of the idea now behind the multi-VAR approach. We have 1 through k total individuals, each with some d by d transition matrix. In terms of interpretation, we generally think these people or these data sets are measured on the same variables, for instance. But the idea is that for each individual's transition matrix, so the matrix that holds those autoregressive and cross-regressive effects, here bk, we're going to decompose that into a component that's common to all individuals, and then this unique component that is unique to each individual in the sample. And so where the lasso and kind of the idea of structured penalties come in here is that we can use these tuning parameters, lambda1 and lambda2k, to essentially govern how much impact that has on the final solution, how much each component drives the final solution. So, I'll kind of give some examples here of some potential situations that might arise to kind of point out how this actually works in practice. And I'll also give a numerical example that kind of backs that up. Okay, so let's say we're in a situation where individuals share nothing in common, right? It's an incredibly heterogeneous process. There's really nothing to be gained from this common modeling component. In that sense, we think that for large enough values of that lambda1 hyperparameter, essentially we're going to push those common effects matrix to 0, right? And all that's going to be left is the unique component, right? And so we'll be left with a situation where each individual's transition matrix is entirely composed of their kind of unique solution, mimicking the situation where we would just fit an individual level model to each individual's data separately. So that's kind of the idea here. We want something sensible. If people are different, you know, and there isn't anything meaningful to extract, we'd like to not extract it. And so I simulated some data. This is all done using the multi-var package, which is on R, which is an R package that you can get on CRAN. So, right, the idea here is that in the top row, sorry, I realize that font's a little small. In the top row, you have the true matrices. So the first one is the true common effects, followed by kind of the true total effects matrix for individuals 1 and 2, just to give you an example of 2 individuals. So these would be B of 1 and B of 2, for instance, in the notation that we were talking about. So we generate data with no common effects. And then right below each matrix, we can see what we estimate using multivar. We estimate a model where that common effects matrix is close to 0. You can see that there are some kind of false positives in there really faintly. So it's not perfect recovery, but not bad given the kind of smaller, I guess, dimension of this problem. We might also be concerned with the other extreme. So the idea that what if actually individuals share everything in common? You know, akin to the kind of common actually modeling situation where we just pool the data and fit a single model to kind of the concatenated time series from everyone, right? And so in that case, we would hope that this lambda2 parameter, right, would be selected in terms of larger values, driving that idiosyncratic or individual component in delta K to 0. And we'd be left with only a matrix of common effects. And when we look at some generated data to kind of tease apart that exact scenario, we can see that you know, we recover pretty well the common effects matrix, and each person's individual level or final kind of transition matrix is, you know, basically just the common effects matrix. There are some kind of false positives, like I said, in there, very faint. But, and I'll actually talk about that aspect of this in one of the future developments. But yeah, so we recover something akin to fitting like a single model to all individuals in the sample. And then the obviously more common situation, the reality, you know, there's some amount of commonality among people's processes and some amount of kind of unique variation. And here we would hope that lambda1 and lambda2 would be selected to kind of accurately gauge the contribution of each component to the individual's final transition matrix. Now here, when I generate data where half of an individual's non-zero elements are common effects and half are completely unique, you can see we get something that doesn't look too far off the data generating process itself, where we're recovering kind of these group level dimensions of the process, the things we think maybe might be more generalizable. And so I also think when we think about what you can glean from these models, one idea would be that, you know, for instance, developing interventions where you might not be able to tailor too many, to individual kind of participants. You could target kind of some of these common processes that, you know, might be prevalent in more data sets than not. And so oh, sorry. Is there a question?
Yeah, I was going to ask you quickly, Zach, for the estimation process, do you have numbers for minimum number of variables that you can, like, for example, I assume minimum number of time points that you want to see to actually capture these patterns, right? Do you have an idea, rough idea about those numbers? Like you can work with 10 variables, you at least need about 100 time points, something like that.
Yeah, so I have some simulation studies. So this first part of this presentation is actually published. And so I think I looked at like 1030. I'm not sure the exact dimensions, but I'll show some of like those simulation results in a few slides. But I think, yeah, that isn't, I think, a really important question that I'm only now starting to like evaluate in a more comprehensive way. I'll talk about one of the kind of deficiencies of my first simulation that I ran to try and assess this. Okay, and so as you might guess from some of the things I've been talking about, the tuning parameters are quite important here because they kind of govern these different sparsity dimensions. When I was first looking into how to select these, there's not a lot of relevant literature in terms of cross-validating on these like multi-way type data sets, but there is some literature on cross-validation in terms of multivariate time series or univariate time series. And so I kind of looked to those approaches first. The original paper uses this rolling window cross-validation, and I'll show an illustration of that. And then I've also recently implemented a blocked cross-validation in the package. And although you'd think, and you'll kind of see this, that the blocked would have some advantage, I haven't necessarily found that in a real meaningful way yet. But that doesn't mean it's not there. So the idea behind rolling window cross-validation is pretty simple. I'm not sure where I came up with this number. It's in one of the papers to talk about maybe starting with about a third of the data set, right? And so you can think of each of these blocks as a different individual, kind of 1 to k. So you start with about a third of the data set, train on that forecast ahead, one data point, get the forecast error. Do that for the full data set across individuals. So kind of at each iteration, you're extracting that portion of each person's time series, running the models, calculating the forecast error, and then aggregating at the end kind of across the different grid of lambda values that you're looking at. And so one of the kind of complaints in the literature that I found for this model is that essentially where you see these gray, like remove blocks, like it's data that you're not using. So you're not being really that efficient with your data, but what you are doing is you're respecting the temporal ordering. So I think these approaches are like kind of more generally referred to like out of sample or pseudo out of sample type cross-validation approaches, where you're never testing on data before the training data, right?
Is your train test in the slide, the colors, are they switched, or am I misunderstanding? So you take
yeah, yes, yes, yeah, they're switched. Sorry about that. Thank you. Yes, yeah, they're switched. Blue should be train and yellow should be test. That's probably the same there on the next slide. Yeah, okay. The other idea being this kind of block cross-validation, where you can immediately see you're using all the available data at each kind of fold or iteration. But you potentially have this kind of breaking of the temporal ordering of things, although to the degree that you're working with stationary data, that's not necessarily going to be a big problem. You could see, though, one difference between these two approaches would be that depending on like the length of the data set, the length of the time series, sorry, you could start to run into like computational differences where it's just more efficient to use the blocked cross-validation. So the first extension that I'm going to talk about is the adaptive multivar. So one of the kind of big complaints about lasso is that it can, and this is true of adaptive lasso too, that, these are really asymptotic properties. And so in finite sample, like the behavior is not nearly as nice as you might like it to be. With lasso, there can be kind of a preponderance of false positives. So you're not fully shrinking coefficients to 0. So here I generated like a D equals 6, so a 6 series var model. I think this was like 100 iterations where there were 6 non-zero paths in the true data generating model, and then fit the lasso and this adaptive lasso. which I'll talk about a little bit more in a second, to that data. And you can see really what's happening with the lasso is that you see all those kind of jittered points around 0. Like those should be all forced to 0 in an ideal situation, but you're essentially getting a lot of solutions which are close to 0, but maybe not fully shrunk to 0. And so there's lots of kind of data characteristics that affect this. But in terms of my experiences, like just doing practical modeling with these things, it seems the adaptive lasso generally just performs better. I'm sure there are situations where it doesn't, but I just haven't come across them yet. And so the idea with the adaptive lasso is really simple. You essentially use some consistent estimator, some non-regularized consistent estimator. So here, right, we could fit the canonical var using OLS, or even just like the equation-wise var using OLS, and develop these kind of initial estimates of the model parameters. And so what that allows us to do is essentially structure the lambda penalties so that paths that we think are important get a smaller weight, while paths that seem like they might not be important get a larger weight. And so that just kind of increases the sensitivity at which that penalty is applied, right? It's not being applied kind of universally in the same way to every coefficient anymore. And so it's a little bit, whereas I think in the traditional lasso sense, it's a little bit more straightforward. Here, we don't really have these individual level or unique and common components in the data per se. So we can use something like the median effect as kind of the common effect, and then the deviation from that median effect. So as the L1 norm, kind of the penalty structure in the multivar problem is not differentiable, there's no closed form solution to solving the multivar problem. Common ways to solve the lasso problem are coordinate descent. That's pretty much the most common. I would say it's pretty easy to program. It's the implementation that's available in GLMNet, which has like a very fast Fortran based coordinate descent algorithm. Here we initially and in the end pursued a proximal gradient descent approach, which in some ways is similar to coordinate descent. In a gradient descent, right, you're moving more parameters, you're moving all the parameters at once rather than kind of one parameter at a time. But this proximal gradient descent framework is, I think, pretty popular in like optimization right now. And there was some evidence that it was outperforming coordinate descent, given some kind of tweaks that people use to essentially, generate momentum. I think there's a series of papers by Nesterov about like essentially using kind of weighted pass combinations of the gradient to choose the step size. And yeah, there was some evidence from this Nicholson. There's our package called the Big VAR package that uses proximal gradient descent. That's just for a single VAR model, for like a single individual, but he has some nice papers and notes on the difference between the two algorithms for these problems. Proximal gradient descent also allows like a bunch of other penalties. If you can express the proximal operator in a closed form, it's kind of a bunch of kind of plug and play penalties that you could look at. And so, yeah, as I mentioned, I have some simulations looking at this. I looked at time points of 30, 50, and 100, 10 to 20 individuals, 10 to 30 in terms of number of variables. Sparse transition matrices were drawn from a uniform distribution between 0.1 and 9. And then I essentially ensured that the solution was stationary. Now, I thought I was doing a good job of assessing this algorithm at first in how I structured the data generating model. So the idea here was that like for each individual, data was generating according to one of these conditions, like low, medium, or high heterogeneity. So in the low heterogeneity condition, for instance, for any individual, 66% of their paths were common and 33% were like completely unique to them. So no overlap with any other individuals in the sample. And while I think on one hand, this nicely tests in a way the ability to accommodate to different levels of heterogeneity, it's also a little unrealistic in terms of real data, right? Because there's going to be a variation. One path may be shared by 3 people, 5 people, all people. Like it won't be there all or nothing in terms of heterogeneity. So as you might expect, it actually performed quite well. So in terms of sensitivity and specificity, the red is the adaptive multivar. And so I'm sorry, the columns aren't labeled here. They should be the time series length. So that would be 30, 50, and 100 for each of those columns across sensitivity and then specificity. And you can see there's not a lot of variability around the heterogeneity levels, and overall it works pretty well. Again, with the caveat that we're really playing to its advantage here in this simulation. In terms of applied data examples, I have kind of 2 to share. So here, in terms of daily diary data, so we're looking at across 11 weeks, 16 participants provided daily responses to 10 positive affect items and 10 negative affect items. And so these are ordered accordingly. So first 10 are positive, second 10 are negative. And you can kind of see in the group level modeling that you have this clustering within negative and positive affect in terms of the common dynamics. And you can see kind of a buffering effect, I think, of amusement, this cross-dimensional influence. But I thought, yeah, this is kind of a nice illustration of how this might be applied to kind of daily diary data. I also have a larger scale example. So here, some fMRI data where you actually have more variables, so 160 ROIs and only 114 time points. So more variables than time points and across 52 individuals. So if you start kind of thinking about the dimensionality of this problem, it's quite large when you think about kind of aggregating all this information across the different data sets. And here, I thought this is the group level model, and it kind of nicely recovers some of the different networks, which I've just used a line to kind of indicate on the heat map. Okay. So I'm kind of running out of time, so I'm going to try to wrap this up quickly. So extending multivar. One of the problems with this approach is, and I've only kind of realized this recently and using it more, is that the sparsity in individual level transition matrices is not actually directly encouraged. It's induced by the sparsity in the common effect and this unique kind of offset matrix. And so, I think that's fine in some ways, and can, with appropriate kind of like modifications, it may actually have advantages in terms of allowing more types of heterogeneity. I'm not sure, but one problem with it in its current form is that you can essentially have very, very small like remainders in the person's final transition matrix that should be 0, but aren't getting pushed there because there's nothing that's actually inducing any penalty in that final transition matrix. So I thought, okay, well, let's just add a penalty to the offset. So like if those offsets are not 0, like let's if one's 0.3, one's negative 0.3, let's essentially force them to be actually 0. And yeah, you can, maybe surprisingly, you can kind of do this. A negative is that it becomes a much more complicated problem. And so the fuse multivar, this equation right here, this fused version or fused construction, where you have this additional penalty on the offset, actually can't be solved via proximal gradient descent as far as I can tell, in any straightforward manner. I don't think there's a closed form solution for the proximal operator like there is with the original multivar, which is actually just kind of like soft, or like element-wise soft thresholding. Yeah, so I'm still, we've started some work looking at like ADMM approaches for estimating this problem, which there are some examples in the literature for like sparse, diffuse, lasso in the single kind of data set case. But interestingly, that problem can be set up as a generalized lasso problem, where I'm reusing, I guess, D here, but we have capital D, which is essentially like a penalty matrix that's establishing relationships between the different elements of the transition matrix. And so obviously like D, Y, and Z require some type of special structure, which you have to assemble. But when you do that, you can fit this model in this generalized lasso framework using an algorithm that was proposed by Tibshirani and Taylor in 2011, which is great, and it does seem to work, but is not fast at all. And so that's kind of one of the reasons to look. If you have these really large, sparse D matrices, which we have, then it essentially becomes like a really computationally intensive process. And so this is a paper that I'm currently working on now, and I have simulations running right now. I've kind of looked at similar, but maybe a little different range in terms of simulation factors. So number of time points, 50, 100, 200, number of individuals, 30, 50, and 100, and then variables 10, 30, and 50. I may expand this depending on the results, but importantly, I changed like the data generating scheme, which I think is which does create a lot more realistic looking data scenarios. So in here, we're assigning a proportion of variables to different subsets of individuals. So essentially like randomly select 75% people, 75% of people and give them 5% and fill 5% of their total paths. Randomly selected potentially, so this is sampling with replacement in terms of individuals and sampling without replacement in terms of paths. But essentially what you get is like a wide range of heterogeneity where paths are shared by some subset of individuals, but not necessarily by all, not necessarily by none. And so one condition has finished, which I can present right now, which is, or two conditions, time series length of 50 and 100 with 10 variables and 30 individuals. And you can see that this additional penalty is performing exactly as we hoped it would, in the sense that specificity is increasing. So we're seeing fewer false positives, while not really taking any hit in terms of sensitivity or identifying the kind of correct or the true positives in the data generating models. And so, yeah, that's kind of where I'm at with that. The original motivation, right, was just this idea of decomposing group, subgroup, and individual level effects, adjusting to different levels of heterogeneity, and hoping to be amenable to both high and low dimensional data types. Extending this approach to look at kind of structured penalties as graphs. And then future work, I'm interested in exploring some of these ideas in larger modeling contexts that permit more like a different type of model. So structural equation modeling framework is one of my main kind of backgrounds and research areas. So I'm hoping to think about applying a similar idea there. And then, you know, I have some collaborators on this project that were hugely important and helpful. Vladis Papyrus and Young-Hoon Kim from the statistics department at UNC, and Barbara Fredrickson from the psychology department at UNC. Vladis was my postdoc advisor. And so also have a R package for those who are interested in checking it out. Yep, that's pretty much it.
All right, thank you, Zach.
Sorry, squeezed in a lot.
It's interesting. I actually have a question, but before that, I'll go give a few minutes for participants to ask questions if they have any. So my question was going to be that with the dimensions of your data, like you talked about the sparsity of your matrix, but you like, I assume that with the dimension of your data, you will see sparsity in your origin, like the data set itself, right? So you will have missing values. Like if you take the data diet diaries, like let's imagine that one person forgot to record the diet at one given time or something like that. How does that affect your like the estimation process? Or
Yeah,
does
that's a
it
great.
take care of itself?
No, so yeah, like in terms of missing data.
Yeah.
Yeah, that's a huge like problem, that this method absolutely does not actually have a way of handling. So, and the little I've looked into how to treat missing data in terms of like these regularized models, it's pretty difficult because, if you think about something like multiple imputation, where you are potentially going to recover different solutions for different.
It's going to be computationally blown then in that sense.
Well, yeah.
Right. Yeah.
I mean, the multivar approach is actually does not take that long to fit like a single one of these across like the hyperparameters.
Okay.
But yeah, I agree. I think, yeah, there should be us. So if anyone has ideas on that, I'm really like open to them, because the little bit I've looked at it, like nothing immediately jumped out at me as being like seeming sensible as a way to like handle missing data in these variable selection with these variable selection techniques.
Okay, cool. All right. Well, thank you again. I appreciate it very much. And I hope to see you in May, I guess.
Yeah, for sure.
Learn more about it.
Thank you very much.
Yeah. All right. Thank you, everyone.